Okay, guys, this is section 3 of chapter 4. This is it for this chapter. And I want you to consider this question. When you add sugar to coffee, tea, iced tea, or lemonade, the sugar disappears. What do you think happens to the sugar? So if you're thinking about each of these individually, right? Coffee, if you're thinking about coffee, tea, or iced tea, or lemonade, maybe different things are going to happen, right? We'll kind of come back to that in a minute. So just jot down what you think is going to happen to each and why. So let's say we're talking about mixtures. So we moved on from compounds. So compounds are a different idea, and now we're talking about when we combine elements and substances in a different way. So a mixture is a combination of two or more substances that are not chemically combined. So think about going back to chapter 2 when we talked about chemical changes and physical changes. There are no chemical changes when you make a mixture. Okay, so it's like taking two ingredients, mixing them together without changing those actual two ingredients themselves. So when this happens, when you make a mixture, nothing new is formed. Okay, so no new chemical substance is formed, right? So let's stop right here and make sure we understand the difference between a compound and a mixture. This is a key difference here for understanding chapter 4. So when we take a compound, there's the chemical bond, right? So there's this bond in the substance. It is it's a semi-permanent bond, right? And it is it is different from mixture. So a chemical change, rather, is needed, right, to separate a compound. But you do not need a chemical change to separate a mixture. All right. So if you think about the bonds that hold water together, you can separate hydrogen and oxygen, but it takes a chemical change. It takes a process called electrolysis to separate those two things, but not so in a mixture. So there's different ways to separate mixtures. You can still separate them. You have to do it physically, right? You actually have to separate the substances. So when you do that, when you separate, let's say, the sugar from the lemonade, you're not changing the identity of the sugar. You're not changing the identity of the lemon juice and water. You're keeping them all kind of separate. Now, they were mixed together, right? It might be kind of difficult or seem hard, but it's possible. You can do that without any kind of major chemical changes, major heat added, or anything like that. So there's 3 common ways to separate mixtures. So the first is to distill something, right? So we're looking kind of over here, right? So when we distill something, you heat it up. You're basically boiling it away. So if there's a liquid and a solid mixed together, right? So you're going to boil away that liquid till all you have left is a solid. So you can see right here, if you look in closely, you've got your Bunsen burner. You're boiling this liquid away. Now let's say that there's salt mixed in with that, right? All the steam would be carried out through here, through these pipes, and taken away somewhere over here. And what's left is maybe some water vapor here, and all that's left is maybe the salt at the bottom of that container. So that's called distillation. So if you've heard of like a distillery, right, like the restaurant distillery, a distillery is a place that made alcohol, right? And to make alcohol, you actually do the process of distillation. That's how you purify the alcohol and make sure there's no, crap floating around in your whiskey or whatever you're making. And it's a way to kill bacteria too. So that is distillation. You can also use a magnet, right? So if you're dealing with metal, you can use a magnet to separate some smaller pieces of metal from the larger pieces of metal. We may do a little demonstration of this in class soon. You can also use something called the centrifuge. So the centrifuge sort of uses gravity and momentum and to spin a substance, usually a liquid, and it spins so fast that the different densities separate, right? So here we have plasma up here. So plasma is the part of your blood. I'm not using a pen tonight, so it's kind of hard to write. So plasma is the part of your blood that doesn't have the blood cells, and down here you can see here are the blood cells down here. So they have different densities, right? So when you spin them at a higher rate, they tend to separate based on their densities. The less dense stuff rises to the top, the more dense stuff goes down to the bottom. So you've got this separation, right? So that's another way to do it. You can also use a filter here. It's not kind of on our list right here. Maybe you should add it. So you can use a certain filter, especially if the mixture's got some big particles in it. The filter can be used to separate a substance as well. So all 3 of these things are just physical changes, right? We're not changing the identity of the plasma or the blood or the nails or the salt in the water. They're still kind of their own thing. However, they've been separated, right? So due to that physical change. So the ratio is important, actually, because it's not important, because when you make a mixture, it doesn't matter how much of something you put in there. All right, let's contrast that to a compound for a second. So when you make a compound, let's say H2O, right? Notice there's a certain number of hydrogen atoms that have to be there for it to be water, right? To make this compound, there has to be 2 hydrogens, 1 oxygen. No ifs, ands, or buts. It has to be like that, all right? So contrast that to a mixture. If you're making a mixture of, let's say, water and sugar, again, we use that example, it doesn't matter how much of each you put in. So the ratio is not important. So that's a big difference, between a compound and a mixture. The compound does matter. Ratios matter. Write that down. Ratios matter in a compound, but in a mixture, they do not matter. Okay, they do not matter. So, for example, like granite, a lot of you guys have granite countertops at home. Now, I'd say if you go look at your granite countertop, go to a buddy's house, his granite countertop is probably not going to look exactly the same. That's because there's different ratios of minerals in there, right? And on the next slide, right here, you can see the different kinds of granite, right? So you've got this one here probably has got a little bit more quartz in it, right? This one here's probably got a little bit more of a red mineral there. You've got all kinds of different ones here. This one's called emerald pearl. So they're different ratios, different mixtures. Now, granite is still the main ingredient, but it's mixed with some other stuff here. So here's examples of how these are all different mixtures because of their different ratios of granite and other minerals to provide, those cool colors. Okay, so now we're going to go to a type of mixture, specific type of mixture. So the mixture is sort of the overall idea on the idea chart, right? So now we're going down and we're going to talk about solutions, which is a type of mixture. So it's a mixture that appears to be a single substance. So what that means is it appears to be all the same, even though there's a bunch of different ingredients in it. Okay, so if you think, and I'll read what it says here, the process in which particles of a substance separate and spread evenly throughout the mixture is called dissolving. So when you have a solution, something has been dissolved into a liquid or into a substance. All right, so if you think about Coca-Cola, it looks like it's all just the same, right? It looks like if you pour it, you can look through that brown liquid and it looks like it's kind of one type of substance. But if you look at the ingredients, there's bromine, there is sugar or corn syrup, there's water, there's carbonated, there's carbon dioxide, there's a bunch of different stuff in there. So in that solution, there's 2 parts to a solution. The solute is a substance that is dissolved, and the solvent is the substance in which the solute is dissolved. So let's say we have a container here of a substance, right? All right. So the substance in which the solute is dissolved is kind of like the liquid. Think about it like that. That is the solvent. Okay. And if I sprinkle some, it's kind of hard for you to see these dots here, but if I sprinkle some stuff in it and I put that into the solvent, that is the solute. Okay? So the solute is like the sugar that you're mixing into the Coca-Cola, right, before when you make it. So those are the 2 parts of a solution. Some examples of solutions are soft drinks, like I mentioned, like Coca-Cola, gasoline. Gasoline has obviously the petroleum in it, which powers your car, but it's also got some cleaners and some other detergents and stuff in there too. And tap water. So if you look at tap water, you can pour it from your sink right now. Wow, you look at it and say, hey, that just looks like clear. There's water, but there's other stuff in there too, mixed in. That's so well mixed you can't see it, right? Think about it. There's fluoride in there. There's some chlorine to kill the bugs and germs. So solutions can also be gases too. So air is a solution. There's other stuff besides just oxygen in the air. You can't see it, but it's mixed in very, very well, so there's other stuff there. So there's other gases up in our atmosphere other than oxygen. So you can also have solutions that are solids too. A lot of you guys have already mentioned some of these. So alloys are what we call solid solutions. So we've talked about bronze. So bronze is an alloy, and steel is probably the most common one. All right, so I spelled steel wrong. Oh my God. Steel is an alloy. So steel is iron mixed with some other metals, and bronze is tin and copper mixed together. So when you look at a piece of bronze, you can't tell, right, that it's bronze, that it's copper and tin, but it's there, right? So well mixed together that it appears to be one solution. That's what makes it a solution. And when you look at a solution, there's particles inside, so they're so small that they don't settle. So the word settle out kind of means they don't settle to the bottom. So and you look at the Coca-Cola, the corn syrup doesn't like sink to the bottom because it's so well mixed in, and it can't be removed by filtering. So in the solution, it's so well mixed and it's so mixed well on such a small, tiny molecular scale that that you can't filter it out. So if I pour Coca-Cola through a filter like a coffee filter, I'm not going to be able to filter out the corn syrup. And they're also so small that light passes right through it. So right here we have an example of a solution where light is just passing right through it. See, to the next one. Now this one here, so we'll call that 2. So tube number 2 probably has not as well mixed of a solution, right? So it may be another example of a type of mixture that we'll get to, because it doesn't scatter the light. See, the light gets kind of caught and trapped in there, versus number 1, where the light passes just right through. So how much solute in the solution matters. Okay, so we call this concentration. So the amount of solute that's in the solution determines the amount of concentration it has, right? So we say something's very concentrated if it has a lot of solute in it. If you've ever seen those frozen orange juices that are in the grocery store, right? They're called concentrated orange juice, right? There's a lot of sugar and a lot of orange substance concentrated in that, and then when you add water to it, you actually dilute it, right? So solutions can either be concentrated or soluted. These terms don't tell you how much solution's in there, but just how concentrated they are. So take a look at this. Here's how you calculate concentration. You take the amount of solute and divide by the amount of solvent. All right. So if you've got 35 grams of salt and 175 milliliters of water, divide those two things there. This gives you the concentration. It's pretty much the same thing as density. All right. So something that is really, really dense is going to have a high concentration of whatever the solute is. All right, so let's think about like a milkshake versus a glass of milk, right? So a milkshake has much more concentrated amount of solute. It's much more concentrated than milk, which is more diluted. So solubility is sort of the term that comes from this idea of a solution. So you've heard it before. We talked about it when we talked about physical properties. Solubility is the ability of a solute to dissolve in a solvent at a certain temperature. So some things can dissolve better than others. All right. If you want to tonight, you can take a cup of salt and a cup of sugar and put them into some like warm water. One is going to dissolve more easily than the other. All right. Salt has a higher solubility than sugar. Okay. So the salt, because of its physical properties, you stir just a little bit, will dissolve, right, to create a solution, versus the sugar, which will dissolve eventually, but it takes a little bit more work and probably a little bit more heat to dissolve that sugar. So it is not as soluble as the salts. So solubility of most solids in water increases with temperature. All right, so kind of common sense, right? If you heat something up, things dissolve, or things dissolve more easily. Take a look at this graph, which shows that relationship. So as we go from left to right, we increase in temperature. And you'll notice that as we increase in temperature, the solubility increases in all of these substances. Now, some, like cerium sulfate, it doesn't, but for the most part, they increase as you increase in temperature. So remember that. If you're trying to dissolve a solute in a solvent, just increase the temperature. So gases actually become less soluble in liquids as the temperature is raised. So like gases are, once again, kind of weirdos, and they kind of go backwards. So if you raise the temperature of a gas like cerium sulfate, it actually is harder to dissolve. So you can probably guess why that is, right? We know gases expand when you heat up their temperature, and if they're expanding at a higher rate, it's hard to mix them into another gas to make a substance. So it's better to actually mix gases at cooler temperatures. So if you want to dissolve a substance like a solid in a liquid, right? If you want to take, again, a bucket and put some stuff in that bucket, right? If you want to put it in there, there's 3 ways to dissolve it faster. Mix the solution, heat the solution, crush the solution, right? So kind of common sense, right? If you're mixing some Kool-Aid, that's what you would do. Let's say it's some real crusty old Kool-Aid that kind of is hardened. You would maybe try these 3 things. You would definitely try this and this. You crush it up, but also heating it increases that solubility as well. All right? So the last thing I want to get to, so if we're talking about, we've kind of already gone over, not the last thing, we've gone over solutions. Now the next one I want to kind of, big category we're going to talk about is the suspension. Not a big category. Suspension. So suspension is a mixture in which the particles of a material are dispersed throughout a liquid or a gas, but are large enough that they do settle out. So in this case, it's a little different from a solution. Remember, a solution, the particles never fall and settle to the bottom, right? So the sugar and the corn syrup never settle to the bottom of the Coca-Cola. But in a suspension, the particles are larger, and they do settle to the bottom. So the best example of a suspension is a snow globe. So if you think about a snow globe, if you shake it all up, that snow flies around, but eventually those big particles of snow will settle down to the bottom of the globe. And they also can scatter light because they're big particles here. And you can also take the particles of a suspension and pour them through a filter, and you can take them out, filter them out. The last one, so our last kind of category of mixture is a colloid. Okay, so a colloid is a mixture in which the particles are dispersed throughout, so they're kind of mixed throughout just like a solution, but they're not heavy enough to settle out. So they'll mix all around, but they kind of are suspended up in a solution in the colloid. Okay, so the particles in a colloid are large enough to scatter light. So let's look at this. So in a colloid, if you put your solution in, these particles kind of just hang around and float about in the colloid. Versus if you think about a solution, so that's a colloid. If you think about a solution, they're smaller particles, right? So you actually don't see them. So the substance appears to be all one thing. And then again, compare that to a suspension where the particles are so heavy that they eventually will settle to the bottom. All right. So that's the difference between these three mixtures right there. So you've got your suspension here, you've got your colloid there, and you've got your solution, which looks like it's all just one substance. So the particles here are a lot smaller. So that's it for this chapter. On the next slide is our list of terms that you can use to make like an idea chart or a flow chart for this chapter. I want you to do that in preparation for your quiz, which will be next class. Okay. If you have any questions, shoot me a note on Schoology. There's kind of a lot in this one here. Also, please consult your textbook if you think something didn't quite make sense. It's phrased a little bit differently there and might be helpful for you to read a paragraph or two about one of these topics. Okay, so just be ready for your quiz on mixtures, where we covered solutions, suspensions, and colloids. Some other terms we learned were solubility, okay, and what a solute and solvent are. So make sure you know all that for the quiz. Good luck, guys. And here on the next, are the terms you can use to make your concept map, which is in your packet on the last page. All right, happy studying.